Electrostatic force between the plates of a capacitor. Now we know when we have two plates of a capacitor, they carry equal and opposite electric charges. Now due to these equal and opposite electric charges, these plates attract each other electrically, okay? So between the plates of the capacitor, there is an electrostatic attraction. Why? Because they carry equal and opposite electric charges. So let us assume that we have two plates, each of area A, okay? Let us say we have two plates of a capacitor, each of area A. I'm making the side view of the plates, okay? And say the instantaneous separation between the plates is X and the area of the plate is A. And say the charge on the plate is Q. Of course, one will be plus Q and another will be minus Q. We all know the charges on the surfaces facing each other on the two plates are equal and opposite, okay? Now, since it is a parallel plate capacitor, so if you write the capacitance, it will be what? Epsilon naught A by D. I'm assuming vacuum, so I'm not multiplying with K. Otherwise, had there been any medium between the plates, we have to multiply with K. Right now, I'm assuming vacuum, so it is simply epsilon naught A by D. In place of D, right now the instantaneous separation between the plate is X, okay? So at this instant, you can write the capacitance is epsilon naught A by X, got it? So this is the capacitance at this instant. So this equation is suggesting as X will be changing, so capacitance will be changing, correct? If you are bringing the plates closer, X will decrease, so capacitance will increase. And if you are taking the plates away from each other, X will increase, so capacitance will decrease. Okay. Now, what is the energy of the capacitor at this instant? So if you are writing the energy of capacitor at this instant, so you can write the energy as U, and we can use the formula U is equal to Q square by 2C. Of course, Q will not be changing, correct? Because there is no path for the transfer of charges. There is no cell connected. So Q will remain constant as you are changing X. X is changing. Q will remain constant in this case because there is no path through which Q may change. So if I'm putting the value of C from equation number 2, I'll get Q square by 2 epsilon naught A by X. So I'll get Q square X divided by 2 epsilon naught A, okay? So this is the electrostatic energy stored in the capacitor. Now you are getting the energy as a function of. Now if you want to know the force acting between the plates, because both the plates would be each other with an electrostatic force. So suppose this plate is attracting the left plate with a force Fe. So by Newton's third law, left plate would be attracting the right plate with a force Fe. So find the force Fe, and for that we will apply the concept of the basic mechanics, that force is negative of the derivative of the potential energy with respect to the position. F is minus du by dx. So we will differentiate u, that is Q square X by 2 epsilon naught A with respect to X. Since we already seen that Q is constant, epsilon naught is constant, area of the plate is constant, so what is left is X and the derivative of X will be 1. So this is the expression for the force acting between the plates, Q square by 2 epsilon naught A, okay? So we got the expression for the force acting between the plates. If you simply want to write the magnitude of the force, we will ignore the minus sign. Magnitude of force, okay? So ignore the negative sign. So the magnitude of the electrostatic force between the plates would be Q square by 2 epsilon naught A, and this expression can be remembered as a fingertip point to use it frequently whenever needed. So whenever we can use as a key point or the fingertip point. Whenever we have two plates of the capacitor, one has a charge plus Q, another has a charge minus Q. So they will be attracting each other. There will be an attractive force between the plates. There will be an attractive force between the plates, and the magnitude of the force is Q square by 2 epsilon naught, that is the permittivity of free space, multiplied by the area of the plates. Okay, so this point we can keep as FP. Got it? So this is the derivation for the force acting between the two plates of the capacitor. Okay, now let's see the applications and the problems. Now let's see the analysis on the behavior of the charge and force when your X will be changing. Consider a capacitor. Suppose its left plate is fixed. Okay, this is fixed. It cannot be changed in position. And we have a cell, and this is the right plate, and this is a conducting string, and this point is fixed. Okay, say something like this, and say at t is equal to 0, at t is equal to 0, the charge begins. So of course we know from the fundamentals we have seen in the basic lecture, at t is equal to 0 there will be no charge on the capacitor, and of course there will be a current in the circuit. Already we have seen all these details in the topic of the charging of the capacitor. Now for any time which is here, you see the string will be loose. This is the conducting wire. This conducting wire, okay, from you can say B to C we have a conducting wire, and here the tensile force will be 0 because this plate has no tendency to get pulled at t is equal to 0. Why there is no tendency? Because here the electric force will be 0, as we have seen right now. The force on the attractive force on the plate is Q square by 2 epsilon naught A. Okay, so since right now Q is equal to 0, so the force will be 0. So the right plate is not being pulled by the left plate, so there is no tendency for the string to get intact. This is what at t. Now for any time greater than 0, there will be some charge on the plate, right? The capacitor will be getting charged, and say on the positive plate we have plus Q charge, on the negative plate we have minus Q charge, and the distance between the plate is x. Now since the plates develop some electric charge, so now the plates would be attracting each other, correct? Now the plates would be attracting each other with some electric force, and now this wire which was earlier loose, now it will get tight, it will be under tensile force, and here T will develop, and since this plate is in equilibrium, so T will be equal to Fe. T will be equal to Fe. Now let's see what will be the behavior of Fe and charge on changing X. So capacitance will be epsilon naught A by X at any instant. Okay, at any instant capacitance will be epsilon naught A by X. The charge on the capacitor will be CV. V is the voltage, so Q will be epsilon naught A by X into V. Got it? So you can see as X is changing, Q will change. Okay, now what will be energy, or you can say directly the force? So we have developed the formula for the force, that is Q square by 2 epsilon naught A. So it will be epsilon naught A by Vx whole square 1 by 2 epsilon naught A. So the force at any instant will be epsilon naught square A square V square by X square 2 epsilon naught A. One A will get cancelled away, epsilon naught will get cancelled away, so we'll get epsilon naught A V square by 2 X square. Okay, this is the force at any distance x. Ultimately, equilibrium or steady state will be attained. Okay, or you can say ultimately an equilibrium or steady state will be attained. So say equal to 0, the distance between the plates is d naught. Okay, this is what the distance between the plates at t is equal to 0. Now because of the attractive force would be coming closer to each other, correct? And at capacitor with fully charged, when capacitor will get fully charged, say this is V and this is Q and this is minus Q, this is the say equilibrium state. So if you are making the FBD of the right plate, one force will be acting on it towards left, that is electrostatic force, and one force is acting on it towards right, that is the tension by the adjoining wire. And the plate is equilibrium, so T will be equal to Fe. Got it? Now what is Fe? Now say the distance between the plate at equilibrium is d, and of course d will be less than d naught, correct? D will be less than d naught. What was d naught? D naught was the distance where the charge begins. Now the plates are coming closer to each other because of the electrostatic attraction. So the steady state, when the capacitor get fully charged, say the distance is d, so of course d will be less than d naught because the plates would be now a little bit closer. Now what would be Fe? So right now we have seen when the distance is x, Fe would be epsilon naught a v square divided by 2 x square, and in place of x what we need to keep? We have to keep d. So this will be the force at the steady state. Got it? So you can also remember this as FP. Distance plate is g, when the distance between the plate is g, the voltage applied is V, then the electrostatic force between the plate is what? Epsilon naught a v square by 2d square. Now if at the steady state we have to find tension in the string T, so T would be simply what? Fe, so T will have a value of epsilon naught a v square by 2d square. Okay, so this is how you can find the electrostatic force or the tensile force at the steady or equilibrium state. Got it? So this is the part where we can see how to find the electrostatic force between the plates of a capacitor.